Hey, John here. Let's talk about operator overloading. Well, before we get into the details, let's look at the simple class that I've created to represent a complex number, okay? Now, there's actually a standard complex template class. I decided to call mine CPLX so that the word complex doesn't confuse it with the standard library one, okay? So I'm going to call mine CPLX. Complex numbers have a real part and an imaginary part. I don't use complex numbers very often, so hopefully what I'm telling you about the complex numbers is correct. This is more really about the operator overloading than the fact how a complex number really works. But I'm pretty sure I remember how to add them and subtract them. So what do we got here? We have a real part and an imaginary part. It's just got two private member variables is the real essence here. We have the default constructor here. And we have another constructor that allows us to create one and initialize the values of the two private members with arguments that we pass in. We've got some accessors that allow us to get the real part and the imaginary part if we want. We got a dump routine that just dumps them out and prints out their values. The main routine looks like this. We create a C1 and dump it, create another one, C2 and dump it, give it some values, and then we print it out in the commonly accepted manner, which is the real part followed by the imaginary part. Okay, the show pause, no show pause malarkey has to do with the value that we use, the real number value. If it's positive, we don't want to show the plus. So we say no, don't show the plus, but it will show the minus, okay? Show pause will say show the positive values as well as the negative values for the imaginary part. So you end up with, like, in this case up here, 2.75 and then minus 1i will come out when we print that one out, right? Okay, so let's go ahead and compile that up. Run it. No shock there. We create an object. It's got some private members, and we print them out in the usual way. Now, what do we do here? Well, same code, but what does it mean to add them together? If we want to add them together and create a C3, that is the sum of C1 and C2, we got to do something along the lines of this. We have to add the real number parts together for the new real value, and we have to add together the imaginary parts for the imaginary value. And then, if we want, we can print out the C3, right? So let's go ahead and compile that one. And we can see we got C1, C2, and C3 is the sum of the reals plus the sum of the imaginary parts here. Okay, now let's take a closer look at this. That's a lot of code. What if I have a lot of complex numbers in my program? It'd be nice to not have to write out all this stuff every single time. So what does that really mean? How do we do that? Well, we do it like this. We have our complex number class, just like we saw it before, and now we can just start providing extra functions that the compiler knows about. The C++ language automatically will look to see if a function exists that provides an overloaded operator capability when you're trying to manipulate user-defined object types. The compiler doesn't know how to add two things of type CPLX. It doesn't really know what that thing is. So in order to add them together, I have to tell it how to add them together. So what happens in here? First of all, note that this is not a member of the complex class. This is just a simple function. It's a special one, operator plus. This is a reserved name for a function, all right? Now, I'm not going to write every single possibility out here. We can use the same general approach for the plus, minus, multiply, divide, pipe, you know, the or, the and, the XOR, the modulus, all these what we call a binary operator, a thing that has two operands, one on the left and right-hand side of the operator itself. So this is a reserved word, along with a operator minus, operator star, operator slash, and so on, okay? It has to return a value that is of the type that appears on the left-hand side of this operator here. Now, the compiler is pretty smart. Notice that I've got a complex number and another complex number in this function, and I have an overloaded operator to add two things together. I have a complex number for the left-hand side here, and I have an integer for the right-hand side. Okay, so I can provide as many of these as I want. Maybe I want to add a double, I want to add a float, I want to add a short, or whatever I want to do. I can provide, gazillions of these things, all right? One for every kind of data type. Now, the resulting value is what gets returned then from the overloaded operator. So in both of these cases, I'm going to return a complex, and the value of a complex number, okay? So what do I do here? I'm taking the left-hand side of the operator, the right-hand side of the operator. And you just saw this math below in the previous example. I'm going to create an instance of complex called result. And I'm going to just do the same thing I did in my regular example code and just do the summing right here. The real part summed together, the imaginary sum part together. And I'm going to return the complex object by value, so the compiler can use the resulting value of the addition. And I've got this overloaded one. What if I wanted to add just an int? Okay, same kind of thing. Only difference there is the data type there. And I'm going to add an integer, by the way, to a complex number. The way I believe it works is you add the integer value to the real part, and the imaginary part stays the same. Again, we just return the result. What if I want a unary operator, like I'm negative? Like, what if I want just the negative value of some complex value? Well, I believe you negate the real part. You might have to also negate the imaginary part. I don't know. I haven't used these in 1,000 years. That's an easy enough bug fix. You just reach over here and put a minus over inside here, okay? I honestly don't remember. I'm going to leave it like this. This is not an example on how complex numbers work. This is an example of how operator overloading works. So a unary operator that is a negative sign just simply has the one value. I suppose I should have called it right-hand side, since it technically is on the right-hand side of the negative operator, right? But the name of these variables is actually utterly irrelevant. I could have called it X, Y, and Z, and so on. Okay, anyway, so this thing will be called and given the one single value on the right side of the negative when it is necessary to do so. So if I write a bunch of code like I do down here, here's my C1 and my C2. We saw that before. I'm going to print them out like this. Okay? Instead of adding them together like that, I can just simply say C3 equals C1 plus C2. And because I provided one that also takes an integer, I could just say C1 plus 100. That'll work as well. Or I can say C3 equals negative C3. This will use my unary negative overloaded operator, okay? And again, I just print out the value after each one of these operations. We run it, and we get the outputs that we would expect, right? So when we said C3 equals whatever, C1 plus C2, right? Well, that's the real parts added together. 1.2 plus 2.75 is 3.95. The imaginary parts added together, 3.4i minus 1i is 2.4i, and so on for the rest, okay? So what we've done is we provided the compiler with what it needs to perform addition on a user-defined type that otherwise has no hope in ever understanding how to do that. Now here's something a little bit different. What if we don't want to print it out the way we were doing, right? Let's go back and look at version 3 here again, right? You know, it's nice having the adding and the subtracting. You know, this actually is working very nicely, but I don't want to have to print it out like this. This is a nightmare, right? Let's get rid of that too. We can do that by overloading this insertion operator if we want. And here's how you do that. Now this one's a little bit different because let's make sure I didn't make any changes up here and that I'm hiding on you. No, this is the class up there has not changed in any way. There's my pluses and my unary negative. Here's the new one right here. Overload the insertion operator on cout, or more accurately on any O stream, right? Cout is a type of output stream. Maybe you want to use this while writing to files or writing into a string stream or any other kind of a stream, right? So this is actually more general purpose than just writing the standard out. Now, in order to do this, we have to return a reference to the thing on the left. Okay, look what's going on here. We're providing an overloaded operator that operates on an O stream. We're not editing the O stream class. We're providing the compiler with an additional method that it can use to figure out what happens if I want to do something like cout, double left arrow, C3 or something like that with one of my complex data types to make it easier for me to print these things out. So how then does that work? There's a left-hand side and there's a right-hand side. Notice the right-hand side is constant. It has been all along. And it also is true that the left-hand sides were always constant in these cases up here, okay? Why? Because we're not allowed to touch the operands when we're adding two things together. When you say 5 plus 6, it doesn't modify the 5 and the 6, right? It calculates a sum that represents the sum of 5 and 6. So we're not allowed to modify those two operands. That's why they're const. Well, when we have an insertion operator, we do modify the thing on the left. We are going to actually modify cout by using it and writing data into it by this, okay? So here's what's going to happen. We have a non-const left-hand side. We have a const on the right-hand side, whose type is the thing that we want to tell the compiler how to go about formatting so we can do things like this down here, all right? And inside here, you can see this is the same code we just saw before. Right? So to the left-hand side, whatever that is, the stream that we're given, okay? We're going to do the no-show pause. We're going to write the real out. Then we're going to show pause. I'm going to write the imaginary part, and we're going to put the I after it. Now, we're not going to put endline and all this other junk in here because we don't want to screw it up. We don't know in what context this is being printed. So we're only going to print the value of the complex thing on the right-hand side of the insertion operator. When this is done, we have to return a reference to the left-hand side, okay? Why do we need to do that? Because that's the definition of how this thing works. In order for this to work in format and print C1 to cout, and then for end L to be formatted and printed to cout, this whole thing on the left needs to still represent a reference to a cout object. And the only way for that to happen is for this operation here to return a reference to cout. And the only way for that to work is if this thing here returned a reference to cout. So every time there's an overloaded operator with an insertion operator in it like this, if you look at what's going on, it will return a reference to the stream, okay? That's why this can just keep on going like this, all right? So let's go ahead and compile and run this one. Again, we get the same output we got last time, and but this time, look at what's going on. We don't have all those really long print lines anymore. We can just simply say, hey, print out C3, print out C3, C2, or whatever we want to do. Now notice also we can mix them because we have an operator. We overloaded the plus operator for two complex types, and we also overloaded it for a complex and an integer. And for the unary negative, we can just stick those expressions right inside this stream, just like we do anything else. Like if you put 5 plus 5 in there, it knows how to add those together and take the sum, and then it uses the insertion operator to print those, okay? Now, the only reason it knows how to print the sum of two complex objects is because the operator that adds them together, right here, returns a complex object by value, and then it knows how to print a complex object because we told it to down here, all right? Now, if I don't want to have to call like left get real and get imaginary all the time, okay, and all my overloaded operators, what I can do, I can make those friends, right? Friends can have direct access to the private members up here, okay? So we don't necessarily have to have these. What if I don't have them at all, right? Well, I can just simply make all of these things friends, and that's easy enough to do. We saw that before. Let's see what's going on down here. I just simply declare every one of them that I want as a friend. Make the plus and the minuses and the O stream a friend. Now, as I point out right here, we can make the insertion operator a friend of complex, but we cannot make it a friend of OStream. You know, unless we create our own OStream object. It certainly could be a friend of OStream, but it's not. We don't own that. It's part of the library. The library doesn't know anything about our operator or our class. So we can make it a friend of the thing on the right, but we can't necessarily make it a friend of the thing on the left. Sort of a unique thing about this particular one, right? So, and meanwhile, these are all the same otherwise. Let's go ahead and do a diff between versions 4 and 5 so we can see exactly what the differences are here. So what do we see here? The only difference is that we added these lines here to make all those objects as friends. And then in the main routine, what did I do here? In the implementation of each of the objects, rather than calling get real all the time and get imaginary all the time, I can just reach in the object and grab the real value and the imaginary value, okay? So it makes my implementations a little bit shorter, and it gets rid of these accessors. And in this particular trivial example, this is not a big deal. But if you have a more complex object, it may very well be that there are no accessors like the get and the imaginary part, or maybe there are, but they're expensive to call. It might require a lot of code or, validation and things like that are going on in there. And if you write your own overloaded operators, you can validate that code yourself and let them directly access the private parts of the class. So this can run more efficiently in some cases. And then down in the main code, these thingies on the left represent lines of code that were removed to cut down on unnecessary output for that particular example, all right? All right, continuing with this theme. What if we want to provide a relational operator? Okay, well, a relational operator for a complex number would be true if a comparison between two complex numbers is true if the real parts are the same and the imaginary parts are the same. So if I want to say if, like here, C1 equals C2, I need to tell the compiler how to compare those things. All right? Now, in this particular case, C1 and C2 are not the same, so this comparison will fail. All right? I then create a C3 that's a copy of C1. Well, those should be the same, unless I screwed up my copy constructor, but I've used the default. There isn't one in this class, right? It's a simple member-wise copy is going to be done. And then, yes, they will be the same. Therefore, this if should be true, and we should see this get printed out, okay? So let's compile up example number 6. So it does the usual stuff that we've seen all along. And then it asks if C1 is equal to C3, and it says yes. Before that, it asked if C1 is equal to C2, and it was not, right? We could put an else in here, I suppose, to make that more clear. C1 is not equal to C2. And run that one, and clearly we can see that the relational operator to compare the two values is definitely working. Now let's look at the differences between example number 6 and 7. What am I going to do here? This one, I'm going to use a member function rather than a friend. We did a binary plus, and we used a friend function. Now we're going to do the binary minus a different way, and we're going to use a member function, all right? And then down here, what are we going to do? There's the compare if they're equal and so on. That code's going to get removed. And then we're going to simply subtract the two values and print out their difference, okay? So all I'm doing is just adding another binary operator here. That is the subtraction. Now, the interesting thing, like I said, this is a member function, all right? So if the left-hand side of my overloaded operator is going to be the same as the class that I'm creating, I can just make it a member of that class, right? So if I want to subtract something from this, I can do it like this. Otherwise, I can do it the same way I did up here. I could just as easily say friend complex operator minus, constant complex for the left, and a constant complex for the right. Okay? These two are going to accomplish the same thing. All right? It might be cleaner for you to just make it a member function in here like this, is my point. How do you do that? Well, this thing has to return a complex by value, just like it does in the other cases up here. And we have to create a temporary variable to hold what will be the result. And this is kind of tricky. It's not necessarily obvious how that works, so that's why I wanted to throw this in here. How do I create a copy of something using the copy constructor? You could write one that takes a pointer to an object, but if you need to have the value of an object, right? In order to use a copy constructor, we need either a reference or the value of the thing. Well, that star this is the value of the object that's pointed to by this. Okay? This is how you do that. So this creates a temporary instance of complex, which is a copy of this object upon which the operator is, the method is executing. Then I can simply subtract the real and subtract the imaginary and return the result. Okay, I'm pretty sure that's how you subtract two complex numbers. You simply subtract both of the members of the object on the right-hand side from the one on the left. Okay. And then the example code in the diff, we just simply put this guy down here and there. Print out C1 minus C2. C1 is this value up here. C2 is the value right there, okay? So let's go ahead and compile that up. It looks like it's already compiled. No problem, right there, okay? C1 is 1.2 and plus 3.4i. We're subtracting C2 here, which is going to be 1.2 minus 2.5, and that's, negative 1.55. That makes sense. 3.4i minus 1i should be 2.4i. Oh, I'm sorry, minus a negative 1i is then going to be 4.4i. So that worked out. Worked better than me doing it in my head anyway. All right, so let's look at example number 8. So what's the difference between 7 and 8? No code changes at all other than I've added an assignment operator. And then I've used it down here in the main code of example number 8. So let's go ahead and look inside example 8 here. Oops. I don't have a good enough memory to remember all this plus the changes all at once in my head. So these are all the same, and here's our new one. And the comment here is some operators absolutely cannot be implemented with friends. All right, all the ones above so far could all be done with friends. In fact, all of them were, and I just threw this one in, the binary negation, just to show you how you could do it as a member function. But some of these operators you must implement as a member function. So those are anything that includes an assignment, right? So that would be like the equals, or like the plus equals, minus equals, right? So like times equals, and so on. Anything that updates the thing on the left, that makes an assignment to the thing on the left. Now that should make a little bit of sense because of what I said earlier. All of these operators that can be implemented with friends have to have a const for the thing on the left and the thing on the right. Okay? And notice this. This also has to be const. Why? Because it's not allowed to modify this. This has to be comparable to this guy up here. So in order to modify the thing on the left, you have to use this style of overloaded operator, and the only ones that are really allowed to do that are these assignment operators, okay? So how does this thing work? Well, the assignment operator takes a const reference to the thing on the right side, And in this case, I'm going to say, I want to provide a way to assign a complex, an instance of a complex, a number, the value of another complex number. And when it's done, it's going to return a reference to the result. Okay? This is not entirely unlike what happens with this overloaded insertion operator. Okay? But the rules of the C++ language are such that if you need to use an assignment operator, you can only do it with a member. Okay? So what do we got to do here? Well, normally you need to check to see if somebody asks you to assign something to yourself. In this particular case, it wouldn't hurt anything to assign, real equals itself and imaginary equal to itself. But if you have a complicated object that has pointers to buffers and all this other stuff, you may not want to try to copy it onto itself. It's just a waste of time, quite frankly. So no matter what, first thing you need to do is make sure, hey, is the thing on the right side of the operator the same thing? And does it have the same address as this? If so, just return the reference to the thing on the left-hand side of the operator. And that's how you do this, all right? For all the assignments, you have to return a reference to the thing that was assigned. How do you do that when you don't have one? Well, you can say star this, right? This is the address of the object whose member is executing this code. Therefore, star this is the value whose member function here is running, right? And a reference is an alias of that value, okay? So this is how you do that. If you're not trying to assign it to yourself, copy over the parts you want, however you want to do that. Again, this might require a deep copy. We're going to just do a shallow copy in this particular case. And then we return a reference to myself. Down here, right here, we're going to use this assignment operator. Now, I know what you're thinking. What's the difference between this and a copy constructor? Why doesn't it just do the sum, create an instance, and then use a copy constructor to do that? Well, the answer to that question is C1 in this context is not being constructed. Now, C1 was constructed a long time ago, and it has these values in it, 1, 2, and 3.4. What we really want to do is change the value that's inside the object that already exists, right? It already has an address. It already has a location. It already has a place to be. What we want to do is update the value of the C1 object in the place that it already exists. This is a very different operation than saying, give me a C1 and initialize it brand new with some values, okay? That's what's going on here. That's what makes us different. Once I've done the assignment, I can print it out again down here, right? Okay, so let's go ahead and compile up. Example number 8. Oops. And see that running. Okay, so what happened here? What did I do? I added, I forgot what the values were. I added C1 and like C3 or something like that. What am I doing here? C1 equals C2 plus C3. C3 is 10 and 10. C2 is 275 and negative 1. So when we add them together, 275 plus 10 is 1275, and negative 1 plus 10 is 9i. So that goes from here to there. That all makes sense, okay? So this is the general gist of how these things work and why we need to have them. It really boils down to you want to be able to write code using new data types, especially if they represent some form of numeric value. You'd like to be able to treat them like numeric values and add them and subtract them and be able to insert them into cout so you can print them and all that and do all this kind of stuff without writing massive amounts of code for every single time you want to print something out, every single time you want to add something, writing it all out longhand. So what you can do is you can create this library of overloaded operators that say, hey, I'll just deal with it once and for all, debug all these operators, and then from there on forward, you can write nice, simple code that you're already used to. Now, I've gone through a lot of examples in this video here, okay? you can review a lot of this stuff by looking at the example classes that we provided with overloaded operators in the course website that's linked to below this video. This is just really an overview of the whole thing and give you an example of each of the types of operators that need to be overloaded with a little discussion of why we need some of these things to be const and why some of them need to be members, and while other ones could be friends, this one here obviously has to be a friend, right? Because if you want to make it a member, what did I say up here? Is that if, and only if, I should say, when the left-hand side is the same as the class, I could use it as a member function, right? So here's a great quiz question someday. Why is it that this cannot be a member function? Why? Because the thing on the left-hand side of this operator in this particular overloaded function is not the same as the class that's being defined. This is not a complex type on the left here. I could create one that allows me to provide an overloaded operator and insert something into a complex data type if I wanted to. I can do anything I want. Okay, I could make that the same as the equal sign if I really wanted to, and just simply set the thing on the left equal to the value of the one on the right. Okay? If I'm overloading my operators, I'm going to make them do any crazy thing I want. It's advisable, however, not to get too creative with these things and, not leave too far off the beaten path, because your users will never know what the heck to do with them. All right. Anyway, the point of this digression is if the thing on the left-hand side is not the same as the class that you'd like to make it a member of, you can't do it. Okay. So this has to be done as a friend. This here could be done as a member because this is the same as the class I'm defining here. And then one example I gave you here is the binary negative, right? So the left-hand side of this operator in this example is the same as this, okay? And the right-hand side could be anything I wanted to. I could create another one of these and make this an int, just like I did up here for the plus, right? What if I want to subtract an int from a complex number? Well, I'd just create another overloaded function down here, and I would change this to int instead of real, and I would do whatever's appropriate down here, okay? So there's my introduction to operator overloading, a couple of examples of why you might want to do it. And if you want to see examples of, all the operators and how each one of them is supposed to work, go follow the link in the description below this video, back to the course website where we've got a whole bunch more examples and a narrative on each one of the types. Because you're probably not going to remember everything 100% by watching a half-an-hour lecture on this subject. You're going to need reference materials. So when the time comes, you know where to find it. Thanks for watching. See you next time.